Hello everyone, this is Connor. Today I'll be going over the 2015 AP Chemistry Free Response question number 1. So let's get into this. First, oh sorry, this is from a previous recording I did. Alright, so let's see what we have here. Metal air cells are a relatively new type of portable energy source consisting of a metal anode, shown right here, and an alkaline electrolyte paste, right here, that contains water, and we have a porous cathode membrane that lets oxygen in from the air. This will be very important for a question coming up. But all this really means is that the cathode is made of holes and it works by having oxygen come in. See the reduction potentials for the cathode right here. That's the reduction potential for that cathode. And three possible metals are given in the table below. So here, three possible metals. Okay, let's get into the first part. All right, A. Early forms of metal air cells use zinc as the anode. Zinc oxide is produced as the cell operates according to the overall equation below. Okay, makes sense. Using the data in the table below, calculate the cell potential for the zinc air cell. So, looks like we'll be looking at these two. Actually, let's maybe do a different color, maybe. These two formulas, half reactions. And know we have to flip at least one of them. And clearly that's going to be the zinc one, since we need the zinc solid on this side. And when we do that, we negate this. But we also need to multiply this equation by 2. But we know that, and then we multiply this by -2. This only just gets negated. So now we have our two values here for our cell potential, since we need to calculate the cell potential for part A, part 1. And that would be, look at it again. It's 1.31, yep, times plus 0.34. 31 volts plus 0.34 volts, which is equal to, quick maths, 1.65 volts. Sounds good. All right, let's move on to part 2 of this part 5-part question already. This thing is for part A to part E. Yep. The electrolyte paste contains OH minus ions. Okay. On the diagram of the cell below, draw an arrow to indicate the direction of migration of OH minus ions through the electrolyte as the cell operates. So instantly, I'd like to treat this electrolyte paste as almost as if it was the salt bridge, and OH minus ions would go towards, since they are anions, would go towards the anode, which means it would go to the left. That's where the arrow was from before. Yes, I've done multiple recordings of this already. Everyone keeps coming to my room every time I record this. Anyways, let's look on the part B. A fresh zinc air cell is weighed on an analytic balance before being placed in a hearing aid for use. As the cell operates, does the mass of the cell increase, decrease, or remain the same? So after thinking about it for some time, I know the answer should be increases. Now I'll get to why for part 2 of this. Now you think about it, if this equation carries out, which it should, we would get, well, let's start for the full explanation. O2 gas, right, will react. Well, this is from the air. O2 gas we specify from the air, because that's how this cell works, which is why the cathode is porous, will react with zinc solid to produce, which from the equation above, as you can see, zinc oxide. Hopefully that's correct, zinc oxide. And then I think it should be obvious that the mass of zinc oxide is greater than the mass of zinc. Therefore, the weight increases. Great. Okay. Now let's move on to part C, which is another, I think, please a two-parter. Yes. So the zinc air cell is taken to the top of a mountain where the air pressure is lower. Okay, so now we know we're dealing with gases and pressure now. Will the cell potential be higher, lower, or the same as the cell potential as at the lower elevation? So have some thought. Maybe you're thinking about it, trying to work down your head. You should probably say it is lower. Now, why would that be? How does even pressure work into this problem? Well, I'll tell you. Now, first, when I think of pressure, I think of partial pressures. And we know that in this case, for partial pressures of an equation, we want to look at the gases here. So, only gas here is in the reactant side, and it's O2, oxygen, right? So in this case, I want to look at the Q value. And the Q value is equal to the partial pressures of the reactants over the partial pressures. I'm sorry, that is not correct actually. Sorry, that is my fault. Of products. Yes, products of reactants as it always is. Reactants. Okay, in this case, none of the products are actually gases, so if we're thinking about that, that should just be 1 over reactants. Only one reactant as a gas, and that is the partial pressure of the O2 gas. Great. Now that we see from the previous problem, well, sorry, from this problem, it says the air pressure is lower, which must mean that this partial pressure lowers. And this partial pressure lowers, that means the Q value increases. And we know that the cell potential is equal to the standard cell potential minus RT, let me make sure I'm getting it right, yep, and times Faraday's constant times ln Q. Great. So which must mean if Q increases, then ln Q increases, which must mean this decreases. Right. So now we can write, since the partial pressure of O2 decreases, I think I should have referred it differently, but due to lower air pressure. Sorry if I'm ugly handwriting. This is really hard to do on my touch screen with this little thing here. Um, due to lower air pressure. Um, and since Q is dependent, oh, let's erase that. What that's supposed to be. And Q is dependent on only PO2, then Q increases, which means the cell potential, I'll get rid of as I could. The cell potential, let's just move it down a bit lower. So it's a little laggy. It means the cell potential, I'll just do a little abbreviation, is lower. Great. Okay. Yeah, that looks ugly. So sorry for that. Hopefully my voice can make up for that. Now let's move to the next question. Let's highlight for this one because it seems like it's a long question. Metal air cells need to be lightweight for many applications in order to transfer more electrons with a smaller mass. Sodium and calcium are investigated as potential anodes. Okay, remember those from the table above. A 1 gram anode of which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of the cell? Just write your answers. Now, if I actually look at this right now, actually, I don't think I really need the highlighter there. I think I look at my notes here. Looks like I'm gonna need a bit more room. I think that should be fine. Okay, so let's look at these right now. So we know that the equation for the sodium, if you look at the table above, I have it right in front of me actually right now. I know the equation is N for sodium. It will at least include sodium. It's Na2O solid plus. All of them have H2O in them. Plus how many electrons is it? It's 2 electrons. Yes, 2 electrons results in 2 sodium solid plus 2 OH minus aqueous. So look here, it's a bit of stoichiometry we're using right here. Actually, if I think about it, we can see that we have, let's say we only have, as the problem implies, only 1 gram of sodium. So we know that in 1 mole of sodium, if you look at the periodic table, is 22.99 grams. You could just say 23 actually. That should be perfectly fine. And yeah, sig figs are not a big thing. And then we know that based on this, for every, well, we could say 2 moles of sodium, there's 2 moles of electrons, but supply that would be 1 mole of sodium for 1 mole of electrons. And in the end, that should equal to 0.0433 moles of electrons. Okay, cool. Now let's look at calcium. Look at calcium. Let's look at this. And then again, I have the problem next to me. You probably need to flip back to see that problem again. We'll see. Let me see the table. Plus H2O liquid plus, I think it's also 2 electrons. Yes, it is. And calcium solid plus 2OH minus aqueous. Okay, now here we get again, we'll consider we only have 1 gram of calcium right here times, so we know that for 1 mole of calcium, there is, for 1 mole of calcium, there is 40 grams of calcium. And then if we look at the equation above, we know for every 1 mole of calcium, there's 2 moles of electrons, which in the end should give us about 0.050 moles of electrons. Like you can see here, so using the calcium would clearly give us more, well, sorry, what the question is asking for here is of 1 gram anode of which of these metals would transfer more electrons. And clearly, right here, calcium is transferring more electrons here, more moles of electrons, which must mean the answer is calcium. Ca. Box that in. Great. And now we're almost done. The only common oxide of zinc has the formula zinc O. Okay. Write the electron configuration for a zinc atom in the ground state. For this one, we're going to be looking at our periodic table. Hey guys, so I just found a periodic table online, so I'll be editing using let's say Microsoft Paint. So I'm going to go over it again with electron configuration, visualizing it with the periodic table. So as for always visualize as if helium's over here next to hydrogen. So we're going to go across this sublevel, and that's the 1s sublevel. Then we have right here, that's the 2s sublevel. And oh, sorry, first off, I point out that zinc's over here, so we want to make sure so we can get to zinc. But before we can, go to the 3rd sublevel of S, we must go through actually the 2p sublevel right here. And go across, and then we have the 3s sublevel, and then we have, of course, the 3p sublevel. Go across there, 6 electrons. And then we have right here, that is the 4s sublevel. And to get the zinc, we must go through this sublevel. What is this called? This is actually not the 4D sublevel. It's actually the 3D sublevel. and it's 10 spaces. So that's basically how we would do this problem. Back to the Word document. Okay, so two answers for this one would be either you can write the whole thing out, which I will do right now, 1s2, 2s2, remember it's all based on, if you use the visualization of the periodic table, makes it way easier, in my opinion. 3s2, sorry, so 3p6, and then 4s2, and then we got 3d10. Great. Or I find it simpler since argon, 4s2, and sorry, 3d10. Both of these work as answers. And the last question. From which sublevel are electrons removed when a zinc atom is in the ground state is oxidized? So actually, I would like to refer back to the table above. In oxidation, it means that we are losing electrons here. So think of this equation, flip it around, you're losing 2 electrons in this oxidation in this case, which means that since we're losing 2 electrons here, your first move might be to think, oh, we'll move from the D sublevel. That's not correct. We move first from the 4 sublevel, which means the electrons being removed would be from the 4, oh sorry, the S4S sublevel, yep, the 4S sublevel. And that is the answer. Now we'll go through grade breakdowns and see what credit you will get for each answer. Okay, so for the first question, you only gain 1 point for just getting the correct cell potential. So that's 1 point right there. Doesn't even mention units, but definitely always put units just in case. For part 2 of this, 1 point is just earned for doing the correct arrow from right to left. So right here, see right there? That's another 1 point. Great. For part B, you get 1 point for saying that it's increasing. And then you also get another point for the correct justification, which would be this. This definitely counts. For part C, it's another just 1 point for saying that it's lower. And it's another point earned for saying that justification that relates it to a lower pressure or concentration. You could have said concentration because both of them are interchangeable in this case. We're talking about Q of O2 gas to Q, or a quantitative approach using the Nernst equation, which is we'll use both of them in this case. So that is also 1 point for us. For part D, you have 2 points to earn here. 1 point is finding the correct mole calculations for sodium and calcium. So right here is finding the correct mole calculations right here. This is a mole calculation. This is a mole calculation right here. 1 point for both of those. And the points earned for taking the 1 versus 2 moles electrification. Yes, 1 moles for this part, basically. You get another point for this, considering that. And of course, have the correct answer, please. And then for this one, as I said before, 1 point earned for either one of them. You don't get extra points for saying both of them. I just did it just to show you that there's 2 correct answers here. And another point for saying the correct cell level here. Alright, that seems good, guys. Pretty sure that's everything. I've went over everything. Yep. Thank you so much for watching. See ya.